Today's topic is data types. You could think of these as a key that opens the door to timers and counters, analog inputs and outputs, various control structures, all of which lead to our user-defined function blocks. To understand data types, we need to consider the PLC's memory. And you could think of memory in the PLC as a large array where each element of the array stores one bit of information. Each cell holds a single bit. It holds a 0 or a 1. We make use of these memory locations when we associate them with a particular name. For example, global, Boolean, push button, or Boolean, fault. In these examples, we're accessing bit size memory locations. If we wanted to, we could access larger groupings of memory. And that's what we're going to talk about. We're going to talk about the data types. What do we call this thing when we're accessing many pieces of information at once? Suppose you wanted to store a numeric value. Well, if you had one bit, you could store the number 0 or 1. So 0 or 1. If there were two bits, they could take on the value 00, 01, 10, or 11. We would say we can hold numbers 0, 1, 2, or 3. By the way, this here is called the 2's column, and this is called the 1's column. So you would read this as 2 plus 1. So that's where we get 3. If there were 3 bits, we could store the numbers 0, 1, 2, 3, 4, 5, 6, and 7. If we back up, we see that 1 bit can hold 2 values. 2 bits can hold 4 values. 3 bits can hold 8 values. If we continued this, you'd find that 4 bits can hold 16. 5 bits would be 32. So if we wanted to make a general statement, we would say the number of unique values is mathematically defined as n is equal to 2 raised to the b power, where b is bits. We also define a range of values with a value, which is to say the number that may be held in the memory location, is greater than 0, but less than 2 raised to the b minus 1. You could look at it this way. This is the size of the bin, and this is the numbers that can go in the bin. As an example, consider a 5-bit memory location. You could store n to the 2 raised to the 5th unique values. So there are 32 unique numbers that could be stored in that 5 bits. Those numbers can take on values that are greater than or equal to 0, but less than 31. You'll notice that there are 32 unique numbers, but those numbers take on values between 0 and 31. It's like counting to 5. 0, 1, 2, 3, 4. You have to watch out for that distinction, or you can be off by 1. It's a type of computer error. It's called an OB1. That's all fine, but what about negative numbers? Could you do something with a single bit? The answer is no, because it would take a single bit just to tell you if the number was negative or positive. So there's nothing you can do with a single bit. What about 2 bits? Well, this works. We could think of that as a circle, where we start at 0, 0, move to 0, 1, 1, 0, and then 1, 1. We've gone full circle. We would call this 0, 1. We may as well call this negative 1. But what do we call the one on the bottom? We're going to call that negative 2. So this particular circle goes from 0 to 1 to negative 2 to negative 1. You might ask why we made this negative 2 instead of 2. I would propose to you that this bit right here will be used as a sign bit. So as long as that is negative, we're going to consider it a negative number. So a 1 equals negative. Let's see what we can do with 3 bits. We start out with 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on until we make our way all around the circle. We'll assume this is a decimal 0, a 1, 2, and a 3. And going this way, we'll assume this is negative 1, negative 2, negative 3, and negative 4. Once again, we'll assume this first bit is the sign bit. And if it is a 1, that number will be negative. That implies that this bit here is also a sign bit, where a 0 implies positive and a 1 implies negative. If we were to make a general statement, we would say the value of our numbers will be greater than negative 2 to the b minus 1, but less than 2 to the b minus 1, now we drop down, minus 1. In the previous example, we looked at a 5-bit system, and we saw that it took on values from 0 to 31. That's an example of what's called unsigned. In this example, we're going to use signed numbers. Again, with that 5-bit memory location. Negative 2, 5 minus 1 is less than the value, is less than 2 raised to the 5 minus 1 minus 1. Which means our numbers could take on values between negative 16 and I believe that is 15. If we were to make a wheel, it would look like this. It would have the value of 0, 0, 0, 0, 0 on top and 1, 0, 0, 0, 0 on the bottom, corresponding to the value of 0 and negative 16. If we were to walk in this direction, we would see the numbers increase. So 1, 2, 3, till you get to 14, 15, and then we never get to 16 because it jumps to negative 16. Again, 15 is the largest value that this will hold. If we were to walk this way, we would see all of our negative numbers. So negative 1, negative 2, negative 3, till we got to negative 14, negative 15, and then we hit negative 16. If we continue walking, we would go from negative 16 to 15. Let's recap real fast. So we had unsigned numbers, and we had signed numbers. The unsigned numbers would take on values greater than or equal to 0, but less than 2 raised to the b power minus 1. The signed numbers would take on values greater than or equal to 2 to the b minus 1. You got to remember, there's a negative sign there. So let's write that again. Negative 2 raised to the b minus 1, but less than 2 raised to the b minus 1 minus 1. What about other numbers, such as pi? Of course, that means we're asking about decimal numbers. Without going into too much detail, know that there is a memory location that is broken into 3 different sections. The first is the sign bit, which is no different than what we did up here, where we said the first bit determined whether the number was positive or negative. The next section is the exponent, and the next part is the fractional piece of the number. With 32 bits, a constant such as pi is approximated as 3.141592. With 64 bits, the constant pi is approximated as 3.141592653589793, which should be more than enough precision for just about any application you could think of. So far, we've looked at unsigned, we've looked at signed, and then we've looked at numbers that allow us to store decimals, such as pi. For a variety of reasons, you'll find that our memory is grouped in multiples of 8. We have 8 bits. And there are 2 different types that are stored with 8 bits. We have 16 bits with 2 different types. 32 bits, we need more room for that. 32 bits, and there are 3 types. And finally 64 bits, and there are once again 3 types. We have 8-bit unsigned, 8-bit signed, 16-bit unsigned, 16-bit signed, unsigned, signed, decimal, unsigned, signed, and decimal again. And each of these has a particular name. Rather than write everything out on the computer, I thought it might be a little easier if we went to this chart. At the very top, we see our Boolean data types, a single bit width, and it can take on a number of 0 or 1. Here's the prefix, it's an X. We've seen that before. For example, GX panel lamp. The G means it's global in scope. It's X, which is a Boolean, and then the name was panel lamp. Down here, we have our unsigned short integer, which has a bit width of 8. There's the values, the range of numbers that it can assume. We have the short integer, a bit width of 8. Again, negative 128 to 127. From there, the unsigned integer of width 16. The integer that takes on the negative values. From there, we jump to 32-bit widths, and there are 3 different things we'll see there. We'll see the unsigned, we'll see the signed, and then we'll see something called real. So let's see if we can find those. Here's the unsigned, so that's an unsigned double integer, the prefix of UDI. We have the double integer, that one has negative values, and then we have the type real, and you'll see here that it allows decimal points. The last data types have a width of 64 bits. Once again, there's an unsigned, a signed, and then a decimal. So here's the unsigned long integer. Somewhere up here, here it is. Here's the long integer. And finally, we have the long real type. Again, each with its own prefix. Before we move on, I wanted to circle back to this table, and I wanted to talk to you about these prefixes. Since our very first line of code in this class, I've insisted that you use the prefix X for Boolean. At this point, I expect you to use all of these other prefixes as well. So if you're going to use an integer, make sure there's an I in front of it. You might ask why we're using this Hungarian notation, to which I would say this. First, we're going to be doing a lot of coding that's done outside of the connected components environment. We're going to be using pencil and paper for the quizzes and exams. And I want to see that you understand what the data types are, because when you're outside of the connected components, there's nothing that would tell me that other than the fact that you're using the prefixes. I would argue that it also gives you a better understanding of the user-defined function blocks. Again, we haven't exactly covered those yet. However, we know that they are a block of code and that there's an interface between that block and the outside world. If you use the prefixes surrounding that interface, it's easier to understand what's going on, or at least what the inputs and outputs of that user-defined function block are. And the other reason is I really want you to consider what your data types are. This is especially true when we start walking over to the timers and analog sections that are coming in the next couple of weeks. With that said, let's look at a few examples. One example is the 2080 IF4 plugin module. It is a 4-channel analog to digital converter. You could look at it this way. It is an analog to digital converter. It takes a value 0 to 10 volts DC or a 4 to 20 milliamp signal, and it converts it to a 16-bit value that ranges from 0 to 65535. You might recognize that because 0 is less than or equal to the value, is less than or equal to 2 to the 16 minus 1. Okay, by the way, this slash right here means that there are 16 wires coming out of the analog to digital converter. When we're ready to use the analog to digital converter, we will go to Program, In Map. We'll look for the System I/O, and we'll assume in this case that it's in slot 1, analog input 0, 0. We will send this to an instruction called move, which will move the data to UI raw ADC0. This is a local memory location, and it is an unsigned integer. From there, you will take the unsigned raw ADC0 and send it to an instruction called any to real. That will then send the data to global real raw ADC0, which can now be used by your control program. This is another example I thought you might be interested in. On rung 1, we have a global Boolean called push button, that goes through our trigger to make a pulse. So every time the push button is initially pushed, we'll get a single pulse here. Rung 2 picks up that pulse and is used to enable this adder. The adder will add 1 to this thing called short integer count. Remember, short integer only has a width of 8 bits. The result is stored in short integer count. You could think of this as a read, modify, write operation. Rung 3 is used to reset our short integer count. So if either of these conditions are true, if we are performing the first scan of our PLC operation, or if this global reset button is pushed, then the value of 0 will be stored in short integer count. We can demo this program by opening a window, get it out of the way, and then toggle the push button. So global Boolean push button. If we push it once, we should see that the count increments by 1. Now remember, this was a pulse. You will never see a pulse come out of connected components. All right, so we turn it off, we push it again, the count should go up to 2, and every time we push it, the count is activated. So what I'm going to do now is I'm going to go to local variables, and I'm going to increase this number to 125. That way we don't have to push it all those times. Then we go back here. The button now goes to, or excuse me, push the button, it goes to 126. Push the button again, 127. And we push the button again, and it goes to, wait for it, negative 128. Was that expected? Well, if you go back to your table and you look up what a short integer will allow, it says that the values can be between negative 128 and positive 127. So what we've done is we've wrapped around, right? As we went around the circle, we went to 127, then to negative 128. And if we were to continue, we would now see that the number gets closer to 0. If we were to think about that in terms of this circle, we would say this is 0, this is negative 128. As we go around this circle, we see that the numbers increase. So 0, 1, 2, 3, 4, and so on till we get to 126, 127, and then we hit negative 128. And as we continue on this circle, it goes negative 127, negative 126. Again, when we are using that adder, we are essentially taking a pointer and we're removing that pointer one position every time. To make sense of this, I have to ask you a question. What is 50 minutes plus 20 minutes? And some of you would say 70 minutes, and others of you might have said 10 minutes. Let's see who's right. Let's make a clock face, and we'll start here at minute 50. If we were to add 20 minutes, where would we be? And I think you would agree we would be at 10 minutes. So 50 plus 20 is equal to 10, with the stipulation that we are operating in modulo 60. We're operating in a system that can only hold the numbers 0 to 59, which looks very similar to what we're doing with our binary numbers. Here's an example. Suppose we have a multiplier, and we feed this multiplier the number 250 and 250. And our output is 36, because 250 times 250 is obviously 36. But what was our assumption? Well, first we used unsigned short integers for all of our operations, where the number could take on values from 0 to 255. Here's another way of looking at this. Suppose you had a cylinder. For discussion, let's assume the cylinder has a circumference of 256. Which means if you were to wrap a string around it, that string would have a length of 256 units. Now back to our example. We had two numbers that were multiplied together. So 250 by 250 is equal to 62500. Consider that the length of a string. So how many times could you wrap the string around this cylinder? And the answer is 62500 divided by 256. So you could make 244 turns onto this cylinder. So we had a total length of 62,500, and then we subtracted off 244 times 256, and our answer was 36. Here, 244 is the number of turns, and this describes the length of the turn, or modulo. And this piece is what's left over. And of course, what's left over is what actually gets sent out of this multiplier. Here's that example running in connected components. We have 250 times 250 is equal to 36. You'll notice that these are unsigned short integers. And you can see that by hovering here where you see the type US int. You could also see that in local variables where, let's see, it's this one right here, unsigned int, a value of 250. There's a few other examples in here as well. 200 times 500 is 34,464, which is rather unexpected. 10 minus 20 is 246 when you use unsigned short integers. And 100 plus 30 is negative 126. All of these operations would appear to be broken, but they're not. That is the actual result when you consider the data type. So the computer is doing exactly what you told it to do. Let me tell you, these types of problems are difficult to troubleshoot. If you didn't guard against it, if you didn't consider the range of values that your variable might take, you can find yourself in trouble. As an example, consider a motion control system. So suppose you were using a count to keep track of where the motor was. So it's moving forward, everything is fine, and then all of a sudden it wraps around and the control system doesn't see a positive number anymore. It sees a negative number. So what will happen is it will full force push that motor in the opposite direction, which is certainly not what you intended it to do. There are some things you can do to guard against this type of problem. The first is to be very attentive to your memory locations, and you ask yourself a question: how big will the variable be? And if the variable will ever approach that wrap limit where you jump from positive to negative, then use the next size larger. Some folks will say, you know what, I am just going to use the double integers and not worry about it, which is a reasonable thing to do if you have processing power and time to burn. Because every time you use a very large variable like a double integer, it puts an extra load on the PLC and can slow things down, and in extreme cases can actually consume memory that you might need for something else. Some folks will just make everything a type real, which has the same problem, you end up having a memory and performance penalty. And for some applications, it just doesn't make any difference. For others, it can be a problem. So you'll have to decide that on a case-by-case basis. I'd like to end with a look ahead to the built-in functions. We already mentioned the analog to digital converter. So the ADC, we mentioned that had a 16-bit output that could take on values from 0 to 65535. If we assumed a 0 to 10 volt input or a 4 to 20 milliamp input, we could draw a chart showing the relationship. Here, 0 to 10 volts DC maps to 0 to 65535 with a linear relationship between the two. It's not actually linear, it's stair-steppy, it's discrete, but for our purposes, it's as good as a straight line. A straight line described by the mathematical equation y is equal to mx plus b. In the very near future, we are going to perform this mapping operation in the PLC. Y minus y1 is equal to m by x minus x1. You may recognize that as the point slope equation. And we are going to find a way to implement mathematical formulas like that as part of ladder logic using the built-in functions.